Did you know this? When it comes to fire-related deaths, the majority, maybe nearly two-thirds, aren't actually from burns.
Really? That's surprising.
Yeah, they're from inhaling toxic gases, things like carbon monoxide, smoke, and, well, asphyxiation, basically.
Wow.
It's pretty counterintuitive, right? Sort of changes how you think about fire danger instantly. And that's our starting point for today's deep dive. Welcome to the deep dive, where you're a shortcut to getting really well informed.
And today we're jumping into the really critical world of fire protection and prevention.
Yep, we're pulling our insights from a pretty comprehensive chapter on this exact subject.
Hmm.
Our mission for you listening is to give you a solid but quick grasp of the fundamentals, fire science, the hazards in different materials.
Right, and the principles of prevention, protection, and how we actually put fires out in
Yeah.
buildings, industrial sites, that kind of thing.
You're going to get some really practical, crucial knowledge, stuff to help you stay safe, stay informed.
Okay, so let's unpack this surprising thing about fire deaths. It really does challenge how we usually think about it, doesn't it?
It absolutely does. You picture flames, heat.
Exactly, the immediate visible threat. But it's these silent killers, the
Mm.
toxic gases, that are statistically the bigger problem. Why? What makes them so lethal?
Well, a big part of it is carbon monoxide, CO. It's just so insidious.
Oh, so.
It's colorless, odorless, but it has this scary ability to grab onto the hemoglobin in your blood way better than oxygen does.
Oh, wow.
So even if there's oxygen around, your blood cells start carrying CO instead. It blocks the oxygen transport.
So it literally starves your body of oxygen.
Exactly. Your tissues, your brain, leading to incapacitation really quickly, and then, well, asphyxiation.
That's genuinely chilling. And okay, how do these fires even start? Does it vary?
It does, quite a bit, depending on where you are.
For fatal fires in homes, among civilians, believe it or not, cigarettes are still a leading cause.
Still, wow. Okay, what about industrial places? Factories, things like that.
There, it shifts. Electrical issues become the overwhelming cause.
Huh. Why the difference?
It just highlights the different environments,
Yeah.
Homes, it's more about human behavior, everyday items.
Right.
Industry, you've got complex machinery, high voltage, things running constantly. So electrical faults are just a much bigger risk. It shows prevention isn't one size fits all.
Fascinating point. Okay, let's get back to basics. The science of fire itself. Most people probably know the fire triangle.
Oh yeah, the classic. Fuel, oxygen, heat, you need all three.
Simple enough.
But, for flaming combustion, the kind with visible flames we usually think of, there's actually a fourth piece.
Okay.
It turns the triangle into the fire pyramid. And that fourth element is an uninhibited chemical chain
A
reaction,
chain reaction.
specifically involving these things called hydroxyl radicals, OH radicals. Without that continuous chemical feedback loop, the flame just fizzles out. You won't get sustained fire.
Ah, so it's not just having the ingredients, it's the ongoing process that keeps the flame alive. That's a key detail.
Exactly.
And speaking of starting a fire, ignition. There are different types, right?
Yes. Two main ones to think about. First is piloted ignition. That's
Yeah.
what we usually imagine, an external spark, a flame, something kicking it off.
Like striking a match.
Right. But then there's auto ignition, or spontaneous combustion.
That's the one that seems kind of mysterious. It just starts on its own.
Pretty much, it happens without an external spark. Heat builds up inside the material, usually from slow oxidation of organic stuff.
Right.
The classic example is oily rags packed together. That slow oxidation generates heat, and if it can't escape, the temperature rises until, poof, it ignites itself. Even if the room feels cool.
Right, I've heard about that. Okay, so we know how fire starts and keeps going. Now, what about the fuel itself, the materials? Because obviously some things burn much easier than others. How do we classify, say, liquids?
Yeah, that's crucial. The National Fire Protection Association, the NFPA, they have a clear system. It's all based around the flash point.
Flashpoint. Okay, what's that exactly?
It's the lowest temperature at which a liquid gives off enough vapor to form a mixture in the air that could ignite if you introduced a spark or flame.
Ah, okay, so it's about the vapor, not the liquid itself catching fire.
Precisely. It's the vapor-air mixture.
And I hear flammable and combustible thrown around. Are they the same?
Good question. They're often used interchangeably, but technically no, there's a strict definition.
What is it?
Flammable liquids have a flash point below 100 degrees Fahrenheit.
Mm.
Think gasoline, acetone. They give off those ignitable vapors even at room temperature. Very volatile.
Okay, so they're dangerous even when it's cool?
Exactly. Combustible liquids have a flash point at or above 100 degrees Fahrenheit. like kerosene or diesel fuel.
Hmm.
Still dangerous, obviously, but they need more heat to produce enough vapor to ignite.
Got it. Flammable below 100, combustible at or above 100? But just having vapors isn't enough, right? You mentioned the mixture.
Exactly. That brings us to flammable limits, or sometimes called explosive limits.
Limits.
Yeah. For a vapor or gas to actually burn, its concentration in the air has to be within a certain range.
Okay.
Too little vapor, below the lower flammable limit, or LFL, and the mixture is too lean. It won't ignite.
Not enough fuel.
Right. Too much vapor above the upper flammable limit, or UFL, and there isn't enough oxygen mixed in. It's too rich to burn.
Ah, so there's a sweet spot, like a danger zone in between.
Precisely. That specific band between the LFL and UFL is where ignition can happen.
That's a really important distinction. Now, how do we quickly tell what the hazards of some chemical are? I see those diamond signs sometimes with the colors.
You mean the NFPA 704 Hazard Identification System, the fire diamond?
That's it. What's that all about?
It's a brilliant system, actually. Super efficient communication. It gives first responders, like firefighters, a really quick snapshot of a chemical's main dangers.
Like a cheat sheet.
Exactly.
Yep.
In an emergency, knowing that instantly can be life-saving. It tells them what they're walking into.
So how do you read it? The colors must mean something.
They do. Each quadrant tells you something specific. Blue on the left is health hazard, how harmful it is to breathe or touch.
Okay.
Red, at the top, is flammability, how easily it catches fire.
Makes sense.
Yellow, on the right, is reactivity or instability, its potential to explode or react violently.
And the bottom one, it's usually white.
Right. The white quadrant is for special information. Things like if it's an oxidizer, which makes fires worse, or if it reacts dangerously with water, or if it's as simple as fixing a gas, it gives that extra critical context.
Okay, that's really useful. Let's shift from materials to the bigger picture,
Yeah.
buildings. Designing safety right in. The main goals seem obvious, right? Keep people safe.
Well, yes, protecting occupants is absolutely number one. But the objectives actually go a bit further, especially from an engineering and business perspective.
Oh, like what?
It's also about minimizing property loss, of course, but also ensuring continuity of operations. Can the business recover quickly? Can they keep running? It's about resilience, too.
That's a broader perspective than just escape routes. Okay, so how do designers actually stop a fire from spreading once it starts?
A fundamental strategy is confinement, or compartmentation. Basically, you build fire-resistant boxes inside the building.
Boxes?
Yeah, using fire-rated walls, floors, ceilings, even doors. The goal is to contain the fire to the room or area where it started. Slow it down by time.
Fire rated. How do they measure that? How resistant is resistance?
That's actually measured quite rigorously. Materials and whole assemblies, like a section of wall, get fire resistance ratings.
How are they rated?
In hours. It tells you how long that wall or floor or door assembly can withstand a standardized test fire before it fails, either letting flames through or collapsing.
So a 2-hour rated wall should hold back a fire for 2 hours under test conditions.
That's the idea, yeah. It gives you a benchmark for how long the structure can help contain the fire.
Yeah.
And tied into that is the idea of fire load.
Fire load. What's that?
It's not just how much stuff you have in a room. It's the maximum amount of heat that could possibly be released if all the combustible stuff in that area burns.
Ah, like the total potential fuel.
Exactly. Engineers calculate this to figure out how severe a fire could be in that space. And that helps determine what kind of fire resistance rating the walls and floors need. It's about planning for the worst case heat release.
Okay, now here's something really crucial for, well, everyone. Life safety. Getting people out. You mentioned NFPA 101.
Yes, the Life Safety Code, NFPA 101. It's hugely important. Its entire focus is making sure people can safely get out of a building during an emergency, especially a fire.
Getting people out alive. Makes sense.
And a core concept in the code is the means of egress.
Means of egress. What does that include? Is it just the exit door?
Not just the door. It's the entire path. It has to be continuous and unobstructed all the way from where you are inside to a public way outside, like the street.
The whole path.
Right. It has 3 parts. First, the exit access. That's the path leading to an exit, like the corridor in your office.
Okay.
Second, the exit itself. This is the protected part, usually a fire-rated stairwell or a door leading directly outside. It separates you from the fire.
Like the emergency stairs.
Exactly. And third, the exit discharge. That's a pass from the bottom of the stairs or the exit door out to that safe public way. The whole chain has to work.
And how do they figure out how many exits you need or how big they should be?
That comes down to something called the occupant load.
Occupant load.
It's the maximum number of people that a building or a specific area inside it is designed and legally allowed to hold.
Ah, the capacity.
Right. And that number dictates everything about the means of egress. How wide the corridors need to be, how many exit doors, how big they are, the total number of separate exits required. It's all calculated to make sure everyone calculated to be inside can get out safely and without bottlenecks.
That makes sense. I also heard that the stuff on the walls and ceilings matters too. Interior finishes. I thought that was just decoration.
Oh, it's way more than just looks. Those materials, walls, ceilings, even floors, sometimes are critically important for fire spread.
How so?
They're classified Class A, B, or C based on two things:
Yeah.
how quickly flame spreads across their surface and how much smoke they generate when they burn.
Okay.
Class A is the best, slowest flame spread, least smoke. Class C is the worst. Using a lower rated finish, say Class C instead of Class A, can dramatically speed up how fast a fire grows and fills a space with smoke.
Which directly impacts your time to escape.
Absolutely. Huge impact on life safety.
Okay, we've covered a lot on prevention, containment, keeping fires from starting or spreading. But what if one does start? That's where detection and actually putting it out comes in. The active systems. Let's start with detectors.
Right. Two main types you'll encounter: heat detectors and smoke detectors.
Heat detectors, how do they work?
They react to temperature. Some are fixed temperature. They go off when the air around them hits a specific point, maybe 135 degrees Fahrenheit. Others are rate of rise. They trigger if the temperature goes up really fast, like 15 degrees in a minute. Catches fast-developing fires quicker sometimes.
But smoke detectors seem more common in homes, right? Why is that?
Generally, yes. Smoke detectors usually react much faster to a fire than heat detectors. Smoke often reaches the detector long before the heat builds up significantly.
Those extra seconds matter.
Huge difference. And there are two main technologies for smoke detectors: ionization detectors. They have a tiny bit of radioactive material that ionizes the air in a small chamber. Smoke particles disrupt that flow of ions, triggering the alarm. They're often better at sensing small, invisible particles from fast, flaming fires.
Okay. And the other type?
Photoelectric detectors. They use a light beam. Smoke entering the chamber either blocks the beam or scatters the light onto a sensor. These are generally better at detecting the larger smoke particles from slow, smoldering fires, the ones that produce a lot of visible smoke before flames might appear.
Interesting. So different types for different fire characteristics. Now, if a fire is detected, you need the right tool to fight it. That brings us to the classes of fire, right?
Absolutely essential. You have to use the right extinguisher for the type of fire.
Break it down for us. What are the classes?
Okay. Class A is ordinary combustibles: wood, paper, cloth, plastics, your typical trash can fire.
Got it.
Class B is flammable liquids and gases: gasoline, oil, propane, natural gas.
Okay, liquids and gases.
Class C involves energized electrical equipment. The key here is energized. The extinguishing agent can't conduct electricity, or you could get electrocuted.
Right. Don't use water on an electrical fire.
Definitely not. Once the power is off, it might become a Class A or B fire, but while it's live, it's Class C.
Okay, and there's one more.
Class D. This is for combustible metals. Things like magnesium, titanium, sodium. They burn very hot and react badly with water or other common agents. They need special dry powders.
Wow, okay. Good to know. Now, for buildings, especially larger ones, what's considered the most effective way to actually control a fire once it starts?
Without a doubt, automatic sprinkler systems. If we connect this to the bigger picture of building safety,
Sprinklers. Yeah, I see them everywhere.
they are incredibly effective. They often suppress or even extinguish a fire before the fire department can even get there. They save lives and drastically reduce property damage. It's like having a firefighter ready in every protected area.
And I understand there isn't just one type of sprinkler system.
Correct. They're tailored to the situation. The most common is the wet pipe system.
Wet pipe.
Simple concept. The pipes are always filled with water under pressure. When heat activates a sprinkler head, water sprays out immediately. Standard for most heated buildings where freezing isn't a risk.
Okay. What if freezing is a risk, like in a parking garage or warehouse?
Then you'd likely use a dry pipe system. Here, the pipes are filled with pressurized air or nitrogen, not water.
So how does the water get out?
When a sprinkler head activates, the air pressure drops first. That drop opens a main valve, called a dry pipe valve, allowing water to flow into the pipes and out the open sprinkler. There's a slight delay compared to wet pipe.
Ah, clever. Avoids frozen pipes. Are there others?
Yes. A pre-action system is sort of a specialized dry pipe system, often used where accidental water discharge would be catastrophic, like in a computer room or library.
How does that work? More safeguards.
Exactly. It requires two things to happen before water flows. First, a separate detection system like smoke detectors has to activate. That opens the main water valve, letting water into the pipes. But water doesn't spray yet.
Okay.
Water only sprays when an individual sprinkler head is also activated by heat. It's a double check to prevent accidental water damage.
Very smart for sensitive areas. One more.
The deluge system. This is for high hazard areas where you need a lot of water fast over a large area like an aircraft hangar or a chemical plant.
How's it different?
In a deluge system, all the sprinkler heads attached to it are open all the time. There's no heat-sensitive element in the heads themselves.
All open. So what triggers the water?
A separate fire detection system, similar to a pre-action system. When it detects fire, it opens the main deluge valve, and water rushes through the pipes and out of every single open sprinkler head in that zone simultaneously, floods the whole area.
Wow. Okay, that's serious protection. Now, moving beyond general buildings, what about specific industrial hazards? Any unique protections there?
Definitely. In large open industrial buildings, for instance, you often see roof vents and things called curtain boards.
Curtain boards, like fabric.
No, they're usually metal or fire-resistant panels that hang down from the ceiling. They work with roof vents. The idea is to trap smoke and hot gases in sections, preventing them from spreading horizontally across the entire ceiling space. It channels the smoke upwards towards the vents.
Ah, so it keeps escape routes clearer for longer.
Exactly. Limits smoke spread, helps visibility.
And what's a really common, maybe overlooked cause of fires in industrial settings?
Well, something that happens in workshops everywhere, not just giant factories, is hot work, especially welding and cutting.
Hot work, sparks and stuff.
Precisely. Flying sparks, molten metal slag. They can travel quite far and easily ignite any flammable materials nearby: wood dust, oily rags, cardboard. It's a very common ignition source.
So how do you manage that risk?
The key administrative control is a robust hot work permit system. Yes, a formal written authorization before any welding, cutting, grinding, or other spark-producing work can begin in areas not designed for it. It forces a check. Are combustibles moved? Is fire watch needed? Are extinguishers ready? It makes people stop and think before they strike an arc.
That sounds like simple common sense, but I bet it prevents a lot of fires. It makes you think about home projects too, doesn't it?
Oh, absolutely. That angle grinder in the garage. Same principle applies, just less formal.
Good point. And finally, a really basic but critical thing everywhere, storing flammable liquids safely. What are the essentials?
Number 1, user-proof containers. Proper safety cans, usually metal, with spring-loaded caps and flame arrestors,
Okay.
and store them in designated flammable liquid storage cabinets. These are specially built to contain spills and resist fire for a period.
Not just on any old shelf.
Definitely not. And crucially, when you're transferring liquids, say pouring from a drum into a safety can, you absolutely must bond and ground the containers
Bond and ground. Wow.
to prevent static electricity buildup. Pouring liquid can generate a static charge, just like shuffling your feet on carpet. If that charge sparks, and you've got flammable vapors present.
Boom.
Exactly. Bonding connects the containers electrically so charge can't build up between them, and grounding provides a path for any charge to dissipate safely to the earth. It's a vital, often missed step.
Wow. Okay, we have covered an incredible amount of ground here. Seriously, from the basic chemistry of the fire pyramid.
Yeah, the hidden dangers of those toxic gases.
Right. To all the engineering that goes into buildings, compartmentation, egress, sprinklers.
And even those specific industrial things like hot work permits and grounding, it's a lot.
It really is. So what does this all mean for you listening?
Well, I think it shows that fire safety isn't just one thing. It's this whole system, layers of protection.
Yeah.
And understanding even a bit about how it works, why CO is dangerous, what those diamond symbols mean, why sprinklers are there. It just empowers you,
It empowers you to be safer.
It's exactly to navigate the world, your home, your workplace, with a bit more awareness of the risks and the protections in place.
Well said. And to leave you with something to think about, we talked about fire load, right? That
Okay.
idea of the maximum heat energy stored in the combustibles in an area.
Mm-hmm.
How might thinking about your own fire load, the stuff in your living room, your office cubicle, your garage, how might that change your approach to your own personal fire safety? What's your potential fire load and what could you do about it? Something to mull over long after this deep dive ends.